Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome to finite element methods. In the last class we have learned about stresses. So in the present class, let's learn about strains and the deformations in a deformable object. Strains are the basic things that will induce the stress. When an object moves from one position to another position, the movement comprises of displacements plus deformations. So if you take some object, let us say I have taken this square, and if I apply some force on this, so what will happen is the square might elongate as well as the square might rotate like this. So anything can happen. So when the body is deforming, it comprises of both stretches as well as rotations. So what is the necessity for distinguishing these two especially? What is the main reason behind this? Because any rigid body rotation won't induce stress. That is the basic thing we need to remember. Any rigid body motion, any type of thing, whether it is translation or rotation, it doesn't matter. They won't induce any stress. The only deformations, that is only stretchings or shearings, will induce the stress, not the rigid body rotations or rigid body translations. So that is why we need to be very careful in distinguishing the deformation. How much part of the deformation is rigid body rotation or translation and how much part belongs to the stretching. Deformations can be of many types. If you see, we have learned about torsion, bending, stretching, etc. in our UG. All of them will induce stress. If you see, in the case of torsion, it will induce shear stress. If you remember, if you take some shaft, which is some circular cross section or whatever the cross section it may be, if you impose some torque on this, so what will happen is the shaft will twist, that will induce shear stress on the surface of the shaft. And the bending. So in the case of bending, if you take a simple cantilever beam which is fixed at one end and free at the other end, and if you apply some concentrated load at the free end, what will happen is the beam will deform in this fashion, where the top fibers will be elongated and the bottom fibers will be compressed. So there will be tensile stresses on the top fibers and there will be compressive stresses on the bottom fibers. At the neutral axis, it won't stretch, so the stress is zero at the neutral axis. That is the case of bending. In the case of stretching, that is, if you take a simple bar and if you pull it such that the other end is fixed, so the bar will elongate, that is, the bar will stretch. So in all of these examples, we can see that there is some deformation inside the object due to the loading, where the deformation is inducing some stress. Whatever the sort of stress it may be, whether it may be shear, whether it may be normal stress, it doesn't matter. It is inducing stresses. That is, deformations, all these deformations, torsion, bending and stretching, etc., whatever the combinations of the loadings, whether you can have a combination of torsion and bending and stretching, anything can happen, will induce stress, all these sorts of loadings, but not the rigid body displacements. For suppose, if the same example I have given for the square just now, instead of putting a torque here, if I move this shaft, if I translate this shaft from initial position to the final position simply by an amount of some x, then that won't induce stress. It is simply a rigid body motion. It is rigid body translation. That won't induce stress. That we need to keep in mind. That is very, very important. Rigid body displacements need to be defined correctly, otherwise the strains will be incorrect. That is, while calculating the strains induced in an object, we need to know how much stretchings are happening, how much shearing is happening. Because if we combine these rigid body rotations in the calculation of the strains, that will give us wrong strains. Rigid body rotations won't induce any stresses, so we need to distinguish them properly. So here you can see some object where this is the initial configuration. The initial configuration is denoted with capital X, and this is the final configuration. Let the final configuration be denoted with small x, where if you take some vector here, let us take this is my vector. In the deformed configuration, it will go in this fashion. That means this vector has been stretched as well as rotated. So we need to know how much it is rotating and how much it is stretching. That is the whole thing here. So for that reason, we have assigned a coordinate system here. So let us take some Cartesian coordinate system, our standard coordinate system. So here we are defining something called deformation gradient. It is defined as the deformation gradient is used to separate the rotations and translations with the deformations. So how it is defined? So it is defined as Fij equal to dou small xi by dou capital Xj, where this small xi are the functions of capital X. That is, we are defining our deformations with respect to our reference configuration. Why I am saying that? Because here this small x are functions of capital X, capital X1, capital X2 and capital X3. So if you differentiate those functions with respect to capital X, that is, I am taking my reference configuration, I am differentiating my positions, that is my mappings with respect to the reference configuration. So if I do that, then I am defining this deformation gradient with respect to the reference configuration. So that will become that will looks like a second order tensor. In fact, this is not a second order tensor because this won't obey the transformation rule. So that is why I have represented here as this is small I and this is capital J, which differentiates this small I as the current configuration and capital J as the reference configuration. So if you expand this, dou small xi by dou capital Xj, that is, we are having how many indices, how many free indices we are having here? We are having I and J. I and J are the free indices, where I runs from 1 to 3 and J runs from 1 to 3. That is, I will take values 1, 2 and 3 and J will take values 1, 2 and 3. So based on this, if you differentiate this small x with respect to capital X, then we will get 9 components, 9 individual components. So total components in this F are completely 9, where all the deformation is completely captured by these 9 components, including rotations, stretches as well as rotations, both. So if you see this, how I wrote this, so this is dou small x1 by dou capital X1, this is dou small x1 by dou capital X2, dou small x1 by dou capital X3, where this row is completely comprised with small x. So whatever the small x, so how many functions we are having here? We are having small x1, small x2, small x3, where these are the functions of small x1 of capital X1, capital X2, capital X3. Similarly, small x2 is a function of capital X1, capital X2, capital X3, and small x3 is also a function of capital X1, capital X2, capital X3. Where don't confuse with this capital X, small x1, small x2, small x3 and then brackets. Usually that is a form of representing a function. So what I meant to say is, so this represents a function. It's a function of capital X1, capital X2, capital X3, where that can be of anything. So that can be like, the function can be like capital X1 plus capital X2 square plus capital X3 cube. This is also a function. So with this function, what I can do is, I can differentiate, what is this? This is nothing but small x1. So if I differentiate this small x1 with respect to capital X1, that will be 1. If I differentiate this one with respect to capital X2, that will be 2 times capital X2. With respect to capital X3, that will be 3 times capital X3 square. So at whatever the point I want to find out this deformation gradient, I will keep the coordinates, then I will get the values. So that values I can populate here in this matrix. So in order to repeat again, so this F represents the deformation gradient, where it looks like a second order tensor, but it is not in reality, because one leg of F stays in the reference configuration, one leg stays in the current configuration. So that is why this won't represent as this is not a second order tensor, because it won't satisfy the transformation rules. So this is the complete form of F. So let us learn about what are these rigid body displacements. So if you see this square, so I have assigned a coordinate system here, capital X and capital Y. Now this square has been translated by 5 units in the x direction. So this is one instance and this is another instance. In the first instance, what I did is, I translated this square by 5 units in the positive x direction. So in order to say the mapping of this one, of this motion, how can I represent it? I can represent it as small x is equal to capital X plus 5 and small y is equal to capital Y plus 0. That is, there is no translations happened in the y direction. That is why here I kept 0. Now, while coming to this small x, all the x coordinates have been incremented by 5 units. So that is why the small x is equal to capital X plus 5. So if I want to calculate, so these are the mappings now. So these represent the mapping. So if I want to calculate the deformation gradient for this case, for the first instance, what I can do, I can just differentiate this function with respect to capital X and capital Y, and as well as this small y also with capital X and capital Y. If I do that, that is, if I differentiate this equation with respect to capital X, then the first one will be, the first item, the first term will be 1. Since there is no capital Y here, so if I differentiate this small x with respect to capital Y, that will be 0. Similarly, if I take the second expression, second mapping, y is going to capital Y. So if I differentiate this small y with respect to capital X, that will be 0. And if I differentiate this small y with respect to capital Y, that will be 1. So here, if you observe, this f is an identity. That is, if I operate some vector here, that is, if I want me to write, if I operate this f on some capital X, that will give me small x, where this small x and capital X, they remain as it is. They won't change. So that is the thing here. So the deformation gradient won't change in the case of translation. That is very, very important. So in the case of second instance, if you take here, the x has been translated to 5 units and y has been translated to minus 2 units. That is, it came down. That is why y has been translated to minus 2 units. Now, if you write the mapping for this second instance of translation, that will be small x is equal to capital X plus 5 and small y is equal to capital Y minus 2. And if you write the deformation gradient for this mapping, that will again lead to an identity matrix. So, identity matrix indicates there are no stretchings happening, there are no rotations happening. So obviously it will be as it is, so it won't hurt us at all. Now that is, it won't induce any stress indirectly. So now, while coming to the rigid body rotations, so these are the rigid body displacements or translations. Now the second case is rigid body rotations. So in the case of rigid body rotations, if you see here, again this is my object, this square is my object, that is in the initial configuration. So now I have assigned a coordinate system here, capital X and capital Y, and this square has been rotated by an angle theta. So because of this theta, this is my final configuration. Now if you write the mapping for this type of transformation, that will be small x is equal to capital X cos theta minus capital Y sin theta, and small y is equal to capital X sin theta plus capital Y cos theta. And if you write f for this one, so what is f? F is nothing but dou small x by dou capital X, dou small x by dou capital Y, dou small y by dou capital X, dou small y by dou capital Y. So if you fill these terms here, it will be dou small x by dou capital X will be cos theta and dou small x by dou capital Y be minus sin theta. Similarly, dou small y by dou capital X will be sin theta and dou small y by dou capital Y will be cos theta. So if you say this f, and if you observe this is not an identity. So this will affect our strain calculation. So that is why these rigid body rotations are very, very important while compared to the translations. In the case of translation, we got an identity matrix for f. So it won't come into our calculation. But these rigid body rotations will surely hurt us. That is why we need to calculate how much rotations are happening. That is very, very important. So what is the observation we can take from here? It is translations won't affect f, but rotations will indeed affect f, the deformation gradient. So rotations may be misinterpreted as deformations. That possibility is there. So we need to be very careful. And the next part is the deformation. So the f can be categorized into rotations as well as the deformations. So since I have covered the rigid body displacements and rotations now, the rigid body displacement rotations are over. Now, while coming to the second part, that is nothing but the deformation. So in the case of deformation, let us take an example of stretching. So let us take, this is my initial object, and the initial length will be x and y. The dimensions will be x and y of that square, and this has been assigned with the same Cartesian coordinate system, x and y. So now you have applied some force on this and the body is deformed up to here. So this dotted line will represent the deformed configuration. Well, this is the undeformed configuration and this is the deformed configuration. In the case of deformed configuration, if you see the length of x, that is nothing but 2x. So initially in the undeformed configuration, what is the length here? It is x. Now in the deformed configuration, it is 2x. That is, the length has been increased twice. So if you want me to represent this in the mapping, so what is the mapping here? Small x is nothing but 2 times capital X plus 0 times y. There is no deformation happened in the y direction. That is why it is 0 into y. Now in the case of small y, it is 0 into x plus capital Y. That is, nothing happened in the case of small y. Nothing happened. If you see, the stretching is only happening in the x direction. So this represents the deformation mapping. This is the mapping. Now if you calculate f here, so this is f. F can be represented as dou small x by dou capital X is 2 and this is 0, this is 0 and this is 1. So 2, 0, 0, 1. If you observe this f, it is completely symmetric. So this symmetricity will represent that in this mapping, in this deformation, no rotations happened. So because these off diagonal terms are completely 0, so that is why no rotations happened here, only stretchings happened. And that stretching also, this position will represent how much stretch happened in the x direction and this position represent how much stretch or contraction happened in the y direction. Since if you see this object, the amount of stretch happened in the x direction is twice, that is why we got 2 here. In the case of y direction, there is no stretch or contraction happened, that is why it is 1. This is another thing we need to remember in the case of stretching. What is the other sort of deformation possible? The other sort of deformation is simple shear. Let us take an object. Let us take the same square here. Now you have applied a shear force on one of the face. Because of that, this is the undeformed configuration. That is this is the initial configuration. Now this dotted one represents the deformed configuration. And this is some shear force. Let us say it's some tau. That is a shear force. So if you write this mapping, that will be small x is equal to 1 times capital X plus 0 times y. So nothing happened in the x direction if you see here. So the shearing is happening in the y direction. That is why small y is nothing but 0.5 times x plus 1 times y. So if you observe this mapping and if you write the deformation gradient, it will be, so dou small x by dou capital X be 1 and this will be 0, this will be 0.5 and this will be 1. Now this is the total deformation gradient. And if you observe this deformation gradient, it is not symmetric, it is asymmetric. And there are some off diagonal terms here. So this 0.5 represents there is some rotation happened because of this deformation. So it is asymmetric and represents rotation with shear. So the object is shearing. So during shearing, there is rotation also happen. So that is a very important thing. So simple shear accommodates rotation. Not only stretching, it accommodates rotation. That is very, very important. Second thing, pure shear. The other possible deformation is pure shear. So if you see this object, so now you have applied equal and opposite shears on both these faces. Because of this, this is the deformed configuration. Now because of this, if you write the mapping, this is small x is equal to 1 times capital X plus 0.5 times y and small y is nothing but 0.5 times capital X plus 1 times capital Y. And if you write the deformation gradient for this case, it will be 1, 0.5, 0.51, which is symmetric. So which says that there is no rotations happened in the case of pure shear. But we are having off diagonal terms. So how can we be convinced that there are no rotations happened? So no rotations happened because so equal and opposite rotations happened for this case of pure shear. So 0.5 units of rotation happened in the clockwise as well as 0.5 units of rotation happened in the counterclockwise. That is why the net rotation is 0. No rotations happened. So in otherwise, if you take the diagonals of this pure shear, that is if you take, so let us say these are my initial diagonals of the square. And in the case of pure shear, what happens is one diagonal will completely stretch and the other diagonal will completely compress. So purely there are no rotations happened here. It is completely a stretching process. So this F represents the case of pure shear. General deformations, that is, it's a combination of rotations as well as deformations. So if you take this, so this is the initial configuration and this is the final configuration. Now if you see this, let the mappings will be small x is equal to 1.5 times x minus 0.75 y and small y is equal to 0.5 times capital X plus 2 times capital Y. Now what is F? F is nothing but 1.5 minus 0.75, 0.5 and 2. So this is F. It is neither symmetric, so that is why there are stretchings that happen, as well as these off diagonal terms are not equal. That is, there is some net rotation happened in this deformation. So this represents some sort of general deformations. Usually we tackle with this type of general deformations, where this F will be given and we need to find out how much rotation and how much stretch happened. So in summary, we are having the F comprises of rotations or translations, some rigid body displacements as well as deformations. In the case of the rigid body displacements, we will be having some translations and we will be having rotations. So in the case of translations, the deformation gradient is an identity. So that won't hurt our calculations, that won't hurt our strain calculation. Now while coming to the rotation, it will indeed affect the strain calculation, because we have seen some values are coming in the case of rotation. If you see that, if you remember the rotation, how does the deformation gradient appears? F is nothing but cos theta minus sin theta cos theta for the counterclockwise rotation, where the body is simply rotating but there is no stretching, there is no strains in the case of rotation. So that is one part of deformation gradient. The other part of deformation gradient goes with stretching, simple shear or pure shear. So here the object is clearly stretched and rotated. If you see this general deformation, the object is clearly stretched and rotated, but how much is the stretch? That is the question. So to know that how much is the rotation part and how much is the stretch part, there is a theorem called polar decomposition theorem. So what does it say? One can decompose this capital F into a product of an orthogonal matrix and a symmetric tensor, as F is equal to Ru is equal to Vr. So this R is a rotation matrix which is orthogonal. This is an orthogonal matrix. So how do we define an orthogonal matrix? An orthogonal matrix is nothing but R inverse is equal to R transpose. If the transpose of that particular matrix is equal to the inverse, then that is called an orthogonal matrix. So this R represents the orthogonal matrix and this U and V represents the stretch tensors. U represents the right Cauchy stretch tensor and V represents the left Cauchy stretch tensor, and in which we are going in depth of the continuum mechanics, but this is the basics to define the strain. Strain pops up from here. These are the basics to calculate the strain. The other definition we can introduce here is the displacement gradient. So the displacement gradient is nothing but, first let us define what is the displacement here. As I have already mentioned, this capital X represent the reference configuration vector and small x represent the deformed configuration vector. So this small xi minus capital Xi represent the differences between the components of the vectors of the current configuration and the reference configuration. So that difference will give us the displacement vector. By having this displacement vector in our hand, if we differentiate this displacement vector with respect to the original coordinates, with respect to the reference coordinates, then that can be represented as dou ui by dou xj equal to dou small xi by dou capital Xj minus dou capital Xi by dou capital Xj, where this dou ui by dou xj is a second order tensor and this dou small xi by dou capital Xj is nothing but F that we have defined just now. So dou small xi by dou capital Xj is nothing but capital F and dou small xi by dou capital Xj is nothing but delta ij. If you remember this delta ij is nothing but Kronecker delta. That is, it will pop up a value of 1 if I is equal to j. If I not equal to j, it will be 0. So if you want me to expand this dou small xi by dou capital Xj, how do we calculate this? This small xi is nothing but, or small x1 is nothing but capital X1 and small x2 is nothing but capital X2 and small x3 is nothing but capital X3. So if you differentiate this one with respect to the capital X1, capital X2 and capital X3, then you will get an identity matrix in this fashion. So this represents the identity matrix, this represents the deformation gradient. So the difference between the deformation gradient and the identity matrix will give us the displacement gradient. So if you expand this displacement gradient, how does it look like? Dou u1 by dou capital x1, dou u1 by dou capital x2, dou u1 by dou capital x3. The similar way, dou u2 by dou capital x1, dou u2 by dou capital x2, dou u2 by dou capital x3, and dou u3 by dou capital x1, dou u3 by dou capital x2, dou u3 by dou capital x3. So it will be having complete 9 components. So in the tensor notation, Fij is nothing but ui comma j plus delta ij. And if you remember, this comma represents the differentiation operator. It's a space differentiation with respect to space. So in the shorthand notation, this dou ui by dou xj can be represented as ui comma j. So this displacement gradient is very, very important. We will define strain from this displacement gradient. Thank you so much for watching this video. Stay tuned to Ekeeda. Subscribe to Ekeeda.